Now to the live demonstration. First, I'm going to show how the system would act without conflict resolution. The system is set up in a way that all of the self-management functionalities would create conflicts. I've set the battery levels of the robots to 9%, 7%, and 0% respectively. This results in the withdraw agent trying to send each robot to its depot or its charge station. Next, I set the number of robots on the route to 2. This results in the robots en route agent trying to drive the robots on the route. Or like it tries to drive, 2 robots on the route. Next, I set the required distance from the route to 220 millimeters. So every time there's a free robot, the free positioning agent tries to send this robot to a free position. Finally, the charging station for the robots was set to be inside the route. So over here is the demo. First, I'm going to start by explaining the screen that you see. Over here, we have the battery level of the first robot, the battery level of the second robot, the battery level of the third robot. Over here is the parameter that decides on the number of robots en route. Over here is the parameter that decides the threshold level for the battery, after which the withdraw agent would send the robots to the depot. And over here, I have the free robots positioning distance that's required from the route. Over here, we can see an operative system view of the robots, and over here, we can see a live view of the robots. So I would start by setting the battery level of robot 1 to 9%, robot 2 7%, robot 3 0%, the required number of robots on the route 2, and the distance from the route is 220 millimeters. Notice that over here, coordination agent is disabled. So all of the agents are trying to gain access, and each agent is trying to satisfy its own goal. However, coordination is disabled, which means that the moment the semaphore is unlocked, another agent can gain access and start trying to perform its goal. So this means that each one of the agents try to act one after the other. So it tries to send the robots to a free position, it tries to send the robots to the depot, and it tries to drive the robots on the route. The result is what we see over here. It's a total chaos. Everything is conflicting with everything, and the system isn't even behaving at all. It's behaving chaotically. So the result of not having a conflict resolution is this is all of the agents trying to act on the system and act on each of the robots. And since we don't have any coordination, we have a total chaos. Next, we have the same self-management system using conflict resolution. So again, the system is set up in a way that creates conflicts. In order to compare correctly, I've set the system to the same exact parameters that we've set before. However, now I've included some rules. Because after we have coordination, we need rules to make sure that the coordination is working correctly. So the rules are as follows. The first one is, if the battery level is below 5%, the withdraw agent can act. The second one is, if the battery level is between 5% and 8%, the free robots positioning agent can act. And the last one is, if the battery level is more than 8%, the robots en route agent can act. So again, to the demo. Again, I'm setting the battery level of robot number 1 to 9%, battery level number 2 of robot 2 7%, robot 3 0%, number of robots en route 2, free robots position 220 millimeters. Over here, the coordination agent is enabled. So although all of the agents are trying to gain access, however, the coordination agent still coordinates this access. It uses these rules. So over here now, the battery level for this one is 9%. This rule applies. So you can see the robot is driving on the route over here, this robot. Second robot has a battery level of 7%. So this rule applies, and you can see that it is in a free position. In the third case of the third robot, we can see that the battery level is 0%. So this one is valid. This rule is valid, and you can see that the robot is in its depot. It's in the middle of the position. It's in the middle of the route. So the result of having a self-management system with conflict resolution is the system is behaving correctly. The first robot is driving on the route. The second robot is in a free position. The third robot is in a depot. And we can see the conflict resolution is successful. Now I'm done with the prototyping. Now on to a summary and a brief outlook of the project. To summarize my project, a generic coordination strategy was created. This strategy was evaluated using a prototype. And an extra self-management functionality was created to evaluate the strategy. When it comes to the future of this project, I would suggest creating extra self-management functionalities to further evaluate the prototype and the coordination functionality and the coordination strategy. And I would suggest implementing the coordination strategy in different self-management systems to see its power and its effect. Working on my thesis has given me experience in multiple things. The first one is I had to deal with complex system modification and integration. I had to work in a team. I had to deal with time and project management. I had to work according to the EIS process model. My project was according to the model for conceptual projects. I learned a lot about self-management theory and about agent-oriented software engineering. I also worked using Java and Swing, and I learned Clips and Office. And finally, the hardest experience of them all was trying to wake up early. At the end of my discussion, I really hope that the future system operator would be as happy as Mr. Simpson over here. I would like to thank Professor Göhner for allowing me to do my thesis at EIS. I would like to thank Mr. Mubarak for his endless support and his very good advising. I would like to thank my friends who are sitting over there for their support. And I would like to thank everyone for their attention. And I would like to open the door for questions.